Hello all. It was recently requested that I upload Unit 3, but the A version from 2026. But before I do that, I already have the Unit 3 from January 2026 solved. Therefore, this is what we will talk about today. Okay, so this is Unit 3, Practical Skills in Physics 1 from January 2026, and I'm just going to dive in. And let's start. Okay. Question one. And yeah, the usual thing I always say is that, for example, question one awards, let's see, 9 marks. So this is a problem that should take you about 9 minutes to solve. Okay. So unit 3 lasts for 1 hour and 20 minutes. So you have to time yourself and pace yourself so you are able to finish with all the questions and get the maximum possible marks. Okay, let's start. A student investigated energy transfer using the apparatus shown set up on a bench. So we have a wooden block over here, a glass sphere that rolls down a track, and then there is a plastic cup with a hole that sort of collects the glass sphere, I guess. So the student released the glass sphere at the top of the track. The glass sphere rolled down the track through the hole into the plastic cup. The plastic cup moved the distance d across the bench as shown. So that's the initial position. So once the ball rolls into this cup, the cup moves due to the momentum transferred to it by the ball. Okay. So what's the first question? Let's see. The student used vernier calipers to measure d. She repeated the procedure and the corresponding measurement of d several times. Question I. Describe 2 variables she should control when repeating this procedure. So you have to ensure, that the height, I'm talking about this height that I am marking here with red. Okay, so the height from the floor to the position of the glass sphere, pretty much. Okay, so the height from which the ball is released. Okay. And the other control variable is the distance of the initial position of the cup from the end of the track. Okay, so this distance pretty much. So this is the end of the track, say, and this is where the cup is. So we have to control for this distance. Let's call it S. Okay, so the distance of the initial position of the plastic cup. Okay. From the end of the track. Okay, so control variables are variables that can affect the experiment. Like in this case, if we roll the glass sphere from down the track, for example, the results of the experiment will be different. But we need to find an initial position from which we always roll the ball, and so that the experiment is not affected too much by that variable. Okay, the same goes for the plastic cup. Excuse me. Okay, part 2. Explain what she should do with the vernier calipers, before taking the measurements. So she should pretty much check for 0 error. Okay, so what do you mean by that? She should close the jaws. Okay, and check for 0 error. So what I mean by that is that if you close the jaws and you still have a measurement showing, so maybe you close the jaws and the measurement reads 0.1 millimeters, etc. So that's the 0 error. Okay, so that's that introduces a systematic error into the experiment that we need to make sure that we eliminate. So she should correct for 0 error. to avoid systematic errors. Excuse me. Okay, and systematic errors are errors like that. An instrument malfunctions by, I don't know, some deviations, for example. So any measurement done using that instrument is going to introduce an error. Okay. All right. B. The student investigated how adding different masses of modeling clay to the top of the plastic cup affected D. And I remind you that D is the distance through which the plastic cup moves once the ball is into the cup. Okay. So she puts some mass on top of these cups. That's the idea. Okay. She used the balance to measure the mass of pieces of modeling clay. For each mass, she repeated the measurement of D to determine a mean value of D. The student recorded the following data to plot a graph of the mean D against mass. Criticize the recording of the data. So this is a common question that appears in Unit 3 and Unit 6. This means that you literally have to judge, okay, for example, in this case, we have only 3 measurements, okay, so that's one piece of criticism, okay. Then you see that we have inconsistent figures, for example, in the measurement of D, okay. So stuff like that. So you really literally comment on the quality or the characteristics of your data set, okay. So the first observation here is that we have not enough data to make a plot. Okay. And in general, we need 5 or more needed, right? The second observation is that we have inconsistent decimal points for D. So inconsistent decimal points for D. And the mass range, I mean, if you examine this, the mass range is really small. We need measurements below 16.1 grams, okay? So the mass range, which goes from 16.1 to 18.9 grams, is small, okay? And we need measurements below 16.1 grams. All right. Part C, another student completed the same investigation and plotted the following graph. And we see that we have sort of an inverse relationship. I mean, a relationship of the form D proportional to 1 over m, right? So let's read the question though. The student suggested that there is an inverse. Oh, okay, there you go. Okay, I actually solved this. So this is like a deja vu moment. Or maybe, I already know that this was going to be the question, but I solved this a few days ago, so I forgot. So anyway, the student suggested that there is an inverse relationship between the mean D and the mass added to the plastic cup. Explain how the student should check, if the relationship is inversely proportional. So if D is proportional to 1 over m, then D times m is a constant. Okay. So you can check that. Check by selecting points from the graph. Okay. And forming the product. So for example, here we have, I selected a few data for you. So 19 is this point here. Okay. So 19 grams pretty much times 2.5 centimeters gives you 47.5 grams centimeters. And then the next point over here gives you 18 times 2.6 yields 46.8 grams centimeters, and then 4 times 11 is another point from the graph, gives you 44 grams centimeters. So you see that it's basically an inverse relationship, more or less. Okay, an alternative way to test this, so alternatively, okay, plot b versus 1 over m. Okay, it should be a straight line. So these are all the ways you can test whether the relationship is inversely proportional. Okay, and this was the first question. Okay, kind of long for a first question, but I hope this makes sense. Let's move on. Okay, question 2. A group of 6 students use the pulse echo technique to determine the distance S to a building as shown. And I have to confess that I've never heard of something like this done before. Okay, it's an interesting way of measuring the distance, I have to say, but I've never thought about it. So, question A: one of the students banged 2 wooden blocks together to make a loud sound. The other 5 students each started a stopwatch when they heard the loud sound. A short time later, the students heard the echo of the sound and stopped their stopwatches. The students recorded their measurements in a table as shown. Okay, so those are the measurements. Calculate the mean value of time. So uh, let's just calculate the mean value. Okay, so that bar over there usually means mean. I mean, it's from statistics. So let's add them up. So 0.45 plus 0.51 plus 0.41 plus 0.55 plus 0.49. Okay, and we have a total of 1, 2, 3, 4, 5 measurements, and we find 0.48 seconds. So 0.48 seconds. Determine the percentage uncertainty in the mean value of mean time. First of all, we need to find the absolute uncertainty in the mean value, okay, which is the half range. Okay, and the half range is you take the extreme values. 0.55 is the largest, 0.41 is the smallest, over 2 yields 0.07 seconds, and therefore the percentage uncertainty in the time should be equal to the absolute uncertainty in the time over the mean time itself times 100. I forgot that. Times 100. This yields 14.50. Oops. 14.58 seconds, which we can write. Percent. What's wrong with me? Percent, which we can write as 14.6%. Okay, moving on. Part 3 explain a source of error in these measurements of time. So time delay is one source of measurement. So time delay of error, excuse me. So time delay between hearing the sound, okay, and starting or stopping the clock, and starting or stopping the clock. Okay, so that's one source of error, and this time delay will be different for each student. So the time delay will be different for each student because the reaction time of each person is different. So reaction time, let's say, varies from person to person. Okay, part B now. Another student determined the time between the loud sound and the echo using a microphone connected to an oscilloscope. The screen of the oscilloscope is shown. The horizontal scale represents time. The horizontal scale was set to 50 milliseconds per division, which means that this little box here, okay, represents, oops, it made a trapezium. So basically, the distance between there and there is 0.5 milliseconds. Okay, so this is what it means. Sorry, 50 milliseconds. What am I saying? Something is wrong with me today. So 50 milliseconds per division. Okay. First question I. Okay. Question I. Determine the time between the loud sound and the echo. Okay, so we'll take the center of each pulse, okay, and count boxes. So how many boxes do we have? We have 1, 2, 3, 4, 5, 6, 7, 8. And then if we take the center of each box, we have approximately 8.6. I mean, you can measure the deviations here, right? So you have these small deviations over there. So we have 1, 2, so about 2.5 and 2. So let's say 8.5, okay? So 8.5 boxes times 50 milliseconds per box. Okay, so this cancel in a, I mean, it's a strange unit to use, but it works for us. So 8.5 times 50 times 10 to the negative 3 yields 0.43 seconds, okay, which is the answer. Okay, state the resolution in milliseconds of the horizontal scale of the oscilloscope. So they mean this little division here. So as we can see, we have 5 of those divisions per box. So 50 milliseconds over 5, 10 milliseconds is the smallest resolution. Okay. Determine the percentage uncertainty in the time between the loud sound and the echo. So again, we have to find the absolute uncertainty first. In the time, we will take half the smallest deviation. Okay, so 5 milliseconds. Okay, so the percentage uncertainty in time is going to be 5 times 10 to the negative 3 over 0.43 times 100 yields 1.16%, which you can write as 1.2%, which is small. It's a good percentage uncertainty. Okay, 4. The speed of sound in air is 330 meters per second. Determine the distance s to the building using the value of time determined from the oscilloscope. So speed is distance per time, right? So distance is velocity times time, but we have to divide by 2 because the time we measured is the time the pulse needs to go back and forth. Okay, so we need to divide by 2 because of that. I hope this makes sense. Okay, so 330 times 0.43 over 2 yields 70.95 meters, which is about 71 meters. And I'm gonna put a note here so that 2 need to divide by 2 to account for the fact that the pulse goes back and forth. Okay. All right. Is there another question? Yes, there is a part C in this question. Large distances, such as the distance s to the building, can be measured using a laser distance meter. A laser distance meter uses the pulse echo technique with pulses of laser light. State 2 advantages of using laser light instead of sound to determine the distance. So laser is directional. Okay. There is less interference with other sources, which is something that can happen with echo pulses because they might interfere with something in the air, some sound, etc. Whereas laser is light there is nothing to interfere with, pretty much. Maybe some electromagnetic radiation, but probably not. And another advantage is that light travels further, especially laser light, right? Because you can point it at a distance really far away, so you can measure large distances that way. Okay, this was question 2, a long problem, okay, towards 16 marks. I hope it was clear. Let's move on to the next question. Okay, question 3. A student investigated the efficiency of the small 9 volts DC electric motor shown in the photograph. The axle turns when the motor is connected to a power supply. Okay. Question A. The student determined the electrical power input to the electric motor. Complete the circuit diagram to show the circuit the student should use. Okay, that's the motor. So we need to provide it with a power supply. Okay, so that's the power supply. We need an ammeter, right, to measure the current. And we also need a voltmeter across the motor to measure the voltage. Okay, so that's an okay circuit we can use, I guess. Moving on, part B. The student set up the apparatus shown. 1 kilogram mass was suspended from the axle using string. The student connected the motor to the circuit. The student switched on the motor for a short time. During this time, the motor raised the 1 kilogram mass through a height L. Identify a health and safety issue and how it may be dealt with. So first of all, you can see that there is a moment, like this whole thing can topple over. Okay, so that's a danger there. So maybe you can put a heavy block on the stand to help it stay there. Okay, so we can write that. So stand may topple over. So use a heavy weight to balance it. Okay. Another safety concern is that the string may break. So you can use goggles for that. So string may break. So use goggles. Oops. And another safety concern is that the mass may fall. Okay. So don't put feet under the table, pretty much. So no feet under table. Okay, so they asked for 1. I actually provided 3. So it's an overkill, but hey, I'm supposed to teach here. So, okay. Question 2. The student used the meter rule to measure L. Okay. Describe an accurate method to determine a single value of L using a meter rule. You may include additional apparatus. So, use a set square, okay, to ensure the ruler is vertical. Okay, that's the one thing. You're gonna put a ruler over here, so you can use a set piece to make sure it's vertical. Maybe you can attach a marker to the mass to help you measure L, pretty much. And view the rule scale perpendicularly. Okay, to avoid parallax error. So to avoid parallax error. Okay, part C. The student switched off the motor and returned the 1 kilogram mass to the floor. The student then switched on the motor and immediately started the stopwatch. He stopped the stopwatch when the mass had moved through a height L. He recorded the time T on the stopwatch. He repeated this for different values of L. The student plotted a graph of L on the y-axis against T on the x-axis. The student stated that the efficiency of the motor can be determined from the graph using the formula efficiency is gradient times m times g over IV, where m is the mass, I is the current through the motor, and V is the potential difference across the motor. Explain whether the student's statement is correct. Okay, first of all, let's go to the back of the paper. I'm going to show you something. So, this is unit 2, unit 1. This is what I want to show you. So remember that the efficiency is pretty much the useful energy output or the useful power output over the total power input or the total energy input. So we will use this pretty much, okay, for the power, and you will see how. Let's go back. By the way, I don't comment often on the formulas that they give you on the back of the paper, but they can really help you a lot in solving problems. Okay, so guys, make sure before you feel desperate or you quit on a problem, just go to the back of the paper and check for appropriate formulas you can use. Okay. Okay, so in we will use that efficiency. Okay, is P useful over P input. Now the input is just I times V, okay? The current through the motor times the voltage through the motor gives you the power input of the motor, okay? So that's, I hope that's clear. Now the P useful is the power output we get from this machine. So what is that? It's the gravitational potential energy of the mass, because we use this motor to lift this mass by some height L. So once it's lifted by that height L, it will have a GP, gravitational potential energy, of mgl, right? So to convert that into power, we need to divide by the time needed to lift it, right? So P useful is mgl over T. Okay, I hope this makes sense. And therefore, if we combine all this, we find that the efficiency is mgl over IV times T. Okay, so if we plot, so they say that the student plotted a graph of L on the y-axis against T on the x-axis. Okay, so let's cast this equation in the way the student used it to make that plot. So I'm moving back here in a clean page, and we solve for L. Okay, so L is IV over mg times the efficiency times T. So this has the form y equals mx, right? Where x in the x-axis, the independent variable is T, and L in the y-axis, the dependent variable is L. So we can write this. So this is the dependent variable, and this is the independent variable. Okay, so the gradient is basically I times V over mg times the efficiency. So the student is absolutely correct. Okay, and this is all they ask in part C, right? Yes. Okay, now part D. The student used a distance sensor connected to a data logger to determine I and T. Explain why using the sensor and data logger would improve the investigation. So the data logger measures the height and time simultaneously. Okay, and errors caused by delay in starting or stopping the watch are eliminated. Okay, so basically you have a more accurate experiment that way. Okay, and this was question 3 of this test, also a very long question, and we are ready to move on to question 4. Okay, question 4. The Prince de Broglie wavelength, I always say that because de Broglie came from an old aristocratic family, so he was sort of a prince. Okay, those were the days, guys. I mean, these guys had it all. Like, they were rich, they did physics as a hobby, not as a job. They traveled around. There were lots of discoveries going on. I mean, physics. I mean, they lived in during the birth of quantum mechanics, so there were lots of discoveries. But I have a feeling, because I really like AI and I have done some research in machine learning, I have a feeling that younger generations of physicists may experience something similar when lots of AI models are applied into computational calculations from physics, and maybe they will come up with some new physics and new ideas, etc. So I feel like I was born in the wrong time to be a physicist. So hopefully the next generation will enjoy moments like de Broglie and the other guys enjoyed 100 years ago. So the de Broglie wavelength lambda of electrons is related to their velocity v by the formula, okay, where h is the Planck constant and m is the mass of the electron. Oh, one more thing. De Broglie's PhD thesis was, I believe, 20, maybe 30 pages long. And it was in that thesis, I think, that he introduced this formula, okay? And he got a Nobel Prize for that. So when I say that those were the days, I mean it. My PhD thesis was, I think, 91 pages long, 100 pages with the references and acknowledgements and like that and things like that. So PhD theses in physics are usually between 100 and 200, maybe 300 pages, depending on what you did. Usually experimental physics theses are longer. Mathematics PhD theses are shorter, usually 20 to 50 pages. So anyway, let's move on. So that formula, h is the Planck constant, m is the mass of the electron. The table shows measured values of lambda for corresponding values of 1 over v. Plot a graph of lambda on the y-axis against 1 over v on the x-axis on the grid opposite. So the first thing I do, let me use a clean page to show you, is to find a range for lambda, okay? And the range, let's leave some room, range for 1 over v. So the range for lambda from the data they give us is from 6.01 to 10.38. So that's, if you subtract these two, you find 4.37. So 10.38 minus 4.37 gives you 6.01. So using 0.5 boxes is okay. I mean, it can work. I hope this makes sense. I mean, I tried to make sure that I have enough room to make a nice plot, okay? So the range for 1 over v is between 0.83 and 1.43. And if you subtract 1.43 from 0.83, you get 0.6. So using 0.05 boxes is okay. I mean, it's appropriate, let's say. Okay. So let me show you now what I mean by that. So what I mean is that, for example, since lambda ranges from 6 to 10.4, say, I will use something like this. 6. My deviations, I mean, will be something like this: 6, 6.5, 7, 7.5, 8, 8.5, all the way to 10.5. And for 1 over v, I will start from 0.8, 0.85, 0.9, 0.95, all the way to 1.45. Okay, and we'll see if this works. Or you can also use 0.1 for 1 over v. So you can also use 0.8, 0.9, 1, 1.1, 1.2, etc. So let's go see the plot. Okay, first of all, let's start with the axis. So that's the 1 over v axis. And this is the lambda axis, right? Okay, so this is 1 over v, and the units are, where is it? 10 to the negative 7. Oops. Okay, let me try. So 1 over v, and the units are 10 to the negative 7, and then we have meters to the minus 1 times seconds. And then for lambda, we have 10 to the negative 11 meters. So 10 to the negative 11 meters. Okay, so for the 1 over v, our range starts from 0.83, so we'll start with 0.8 as our first point, so 0.8. And then let's see, shall we use the small boxes, these ones, and make that 0.85, 0.995, 1. It's gonna get tedious, so what I will do actually is I'm gonna use that 0.9, and then 1, 1.1, 1.2, 1.3, and that's let me transfer this down, okay, over there to make space. Okay, so that's 1.3, and that's 1.4, and that's 1.5. Okay, now for lambda, I think this will look okay, so let's start with 6 over there, 6.5, 7, 7.5, 8, 8.5, 9, 9.5, 10, and 10.5 covers all the range. Yes, it does. Okay, good. Let me use green. I'm going to show you 2 data points, and then I will accelerate the video so you see the final plot. Sorry for taking so long. Okay. First, excuse me. Let's use this first pair of values. 6.01 corresponds to 0.83. So 6.01 will be down there. So this is the first data point. Okay. The second data point, 6.65, 0.91. Okay. 6.65 will be 55, 60, 65. Okay. And the other one was, what was it? 0.91. Okay. So 0.91 will be this point. Okay. Now I will accelerate the plot. The video. Okay, these are all the points. Let's draw a line of best fit that passes through all the points. It doesn't have to pass from 0. So something like this looks okay because it passes through most points. And then we have this point to the right of the line of best fit and this point to the left. So that's good enough. Okay. And this is the plot, guys. Okay. Okay, part B. Determine the gradient of the graph. So the gradient is delta lambda over delta 1 over b. So the change in lambda over the corresponding change in 1 over v. So you can use any 2 points you want from the graph. Let's pick, let's use blue, and let's pick this one and this one because they are kind of easy. Okay. So This is delta 1, delta 1 over V. And this distance over here is delta lambda, okay? So delta 1 over V is, let's see how many boxes we have. So 1, 2, 3.5. So this is 3.5 times 10 to the negative 7 meters to the minus 1 times seconds. And then delta lambda is, let's see, 0.5, 1.5 to 2.5, right? We go from 8 to 10.5, so 2.5, actually, let me come over here, okay? So delta lambda is 2.5 times 10 to the negative 11 meters. Okay, so if we go back and plug in, we have 2.5 times 10 to the negative 11 meters over, what was the other one? 3.5 times 10 to the negative 7. 3.5 times, yeah, okay. 3.5 times 10 to the negative 7 meters to the minus 1 seconds. Okay, and let me use my calculator. So this yields 7.14 times 10 to the negative 5 meters squared seconds. Okay, which is our gradient. Okay, cool. Let's move on. Determine the value of h from the gradient of the graph. Okay, for this one, recall that lambda is h over m times v, times 1 over v, excuse me. So the gradient is equal to the mass of the electron times, wait, I went a little bit too fast and I confused myself. So the gradient is h over m, right? So h is m of the electron times the gradient, or 9.11 times 10 to the negative 31. Actually, we wouldn't need some extra space. So let's do cut and let's move to a clean page. Can we do paste? Paste. Okay, great. So there you go. Okay. All right. So times, what was the gradient? 7.14 times 10 to the negative 4, and the units are kilograms meters squared over second, and I will tell you in a moment what kind of units those are. So let's multiply 9.11 times 10 to the negative 31. I'm using my calculator. Times 7.14 times 10 to the negative 4 yields 6.5 times 10 to the negative 34. And then let me work out those units for you. So we have kilograms meters per second, which we can write as kilograms meters squared second squared, and then we need to multiply by second since we introduced second squared in the denominator, and we recognize this as joules. Okay, so this is joules times seconds, just like the Planck constant. Okay, and the Planck constant is 6.64 times 10 to the negative 34, so our value is kind of close. Okay, all right, so this is the h we found. Now let's move to the last question in this paper. A student determined the value of h as 6.54 times 10 to the negative 34 kilograms times meter squared over seconds to the minus 1 over seconds, excuse me, with an estimated percentage uncertainty of 3%. determine whether this value of h is consistent with the quoted value of h. So 6.54 times 10 to the negative 34 kilograms meter squared seconds to minus 1 times 0.03, which is the uncertainty, yields 0.196 times 10 to the negative 34, which we write as 0.2 times 10 to the negative 34 kilograms meter squared seconds to the minus 1. So H max is going to be H plus this uncertainty. So actually, let me raise this. So it's going to be 6.54 plus 0.2 times 10 to the negative 34. So the maximum possible H is 6.74 times 10 to the negative 34 kilograms meter squared seconds to the minus 1. And similarly, the minimum H is going to be 6.34 times 10 to the negative 34 kilograms meter squared seconds to the minus 1. And let's go to the back of the paper and check the quoted value. So the quoted value is, where is it? It's this one, 6.63 actually. I said 6.64 earlier, I'm sorry. Okay, so that's the quoted value. So we can say that the quoted value is within our range. So the student's value is consistent. Okay, this was a little bit of a long paper, I think. If you made it to the end of the video, comment, I don't know, done in the comments too. I don't know, I want to see how many people actually watch these videos to the end. Okay, from the list I have with past papers, I just realized that this is actually just the second Unit 3 video I'm uploading. And I will have Unit 3A coming up, also from January 2026. Guys, it's just me and my sister's office. So I don't know, I hope one day I become rich enough so I will have someone helping me with the solutions and the videos. And as I said 1 million times, I hope that this channel graduates to something bigger than just A-level physics. I want to talk about other physics topics, AI, coding, video games from the perspective of someone who makes them, not someone who plays video games. But anyway, let me know about what you think about these videos, the channel, the way I teach. Please like and subscribe, and more are coming up. Thank you guys for those who are watching, and see you in the next one. Bye.